All right. Hi, everybody. Welcome to our last Talk Math with your friends before our summer break. So the next 2 weeks are summer vacation, and then that's the plan is to follow that up with a live episode of My Favorite Theorem, which you might know as a podcast. During the break, if you're looking for something else to do, I strongly encourage you to check out Prime, the Pomona Research mathematics experience. As a great series of talks that's going on for the next couple of weeks. And then I just want to ask everyone to join me in welcoming Andrew Stacey. Andrew had a life as a higher ed mathematician and is now a secondary maths teacher. And I think we're going to see some really interesting connections between those two. And I've also had some experience in both, and so that's really where my heart is. And so please join me in welcoming Andrew to Talk Math with your friends.
Great. So I put my screen back on. Okay. Are we ready to go? As I said, okay to recording. So
yes, please.
Yeah, great. Okay, so I had this up while we were coming in. Sort of a little school joke there. You have to sit and wait and quietly, and of course, no one ever does. So lots of words that don't mean the same thing over your side of the Atlantic to ours, but here's the kind of translation. My main reason for putting this is I'm going to talk a little bit about the school, what it's like doing maths in school, and it'd be useful for people to know a little bit how it works in the UK. You notice we've got an off by one error between the school years here, but then I guess that's compensated by the off by one error that for us, the first floor is one floor up from the ground floor, and I think for you guys it's the bottom floor. So yeah, off by one is everywhere. Trapezoid, fantastic word. I think you guys win on this one. Whenever I have an American student in my class, I think it's fantastic because it means I get to use the word trapezoid. And I think I've read that for you lot, trapezium is what we just call a general quadrilateral. Anyway, also useful for you guys to know kind of for what I do is the exams that students in the UK take. Everyone has to take the GCSE, or equivalent. The I stands for international GCSE, it's equivalent. And that's age 16, although there are two tiers, two levels, you can take it out, foundation and higher. But everyone comes out with a GCSE of some description. But then that takes us up to sort of the last 2 years of secondary school, and then in the sixth form, which is the last 2 years, then they can choose to take a course in mathematics. But in fact, they can choose to take two courses. We have maths and further maths. But it's important to sort of know that if you're taking further maths, you're also taking maths. So that's two of your courses. And generally people take 3, possibly 4. So if you're going to take further maths, you've got to show a really big commitment to doing maths. So compulsory up to here, and then optional up to there. And I teach secondary school, which takes me from here all the way up to sixth form. Okay, so on with what I'm going to talk about, from clocks to categories. Now, at one point, I sort of was under the impression this was the conference closer. So I had this whole sort of speech of thanks for the organisers, which of course I can't do now because it's not the conference closer. It's more like the season finale. And I'm very pleased to hear that it's been recommissioned by whatever broadcasting body is in control. So we just get the season finale, which of course means we have to have themes coming back from earlier on, and we have to reveal the big bad that's been going on all the way through.
Oh no.
So no voters thanks, but I thought I'd just offer my own sort of round of applause for all the organisers to say thank you very much for putting this together. And this has nothing to do with the fact that this week I learned how to put emoji in LaTeX documents at all. I'm not showing off at that at all. So anyway, thank you very much for organising this. It has been absolutely fantastic to be at these, and hopefully loads of people in the chat are all saying thank you at the same time. Okay, so I'm going to talk about something called category theory, and I would quite like to get a sense from you lot as to where you are on a sort of categorical level. So are we ready for a poll? Can we do the first poll? Drew, you doing that? Yeah, there we go. So we've got which statement sort of best sums up your reaction to category theory. So range right from the never heard it all the way up to I'm a category theorist. Let's see how we get.
So looks like about half of us have voted by now, climbing pretty quickly.
Okay, we'll just get a sense of where we're at. So we seem to be pretty majority. There's a place for it, I guess. I feel like I should break out into song from that, but I'm not sure what song it would be. Okay, a few never heard of it. Oh, I can share results. Does this work? Can you see it? Yeah, BK's nodding, great. So most in this, there's a place for it, I guess. A few category theorists lurking in the background, fantastic. And a few all the way down at the never heard of it. Okay, so do I get rid of that or do you get rid of that? Or is it gone? Is the poll gone? I don't know how these, this is my first time sort of presenting from Zoom.
It's gone.
So you have to be nice to me. It's gone. Okay, I can still see it, but you guys can't. That's great. Okay, so is your sort of 5 levels. And I was trying to think, whatever you're at, I hope there's something for you in this talk. And here's sort of what I hope at the various different levels. So if you've never heard of it, then hopefully you get some idea as to what it's about. I was never very good at it at school. Obviously riffing off I was never very good at maths at school, hopefully not quite so scary as it for. And through, most of you, there's a place for it. Hopefully I show you that maybe there's more places for it than you thought. So anyway, hopefully something for everyone in what I'm going to talk about today. Okay, so I said that we'd be having recurring themes from the Talk Maths with Your Friends series, and the first one I would pick up is actually from last week with that fantastic talk on infinite chess, where Joel said, and I hope I got this right, that part of his interest in it is sparked from a math overflow question. And actually this talk also comes out from a math overflow question, slightly older, way back in October 2010. For those of you who don't know your mathematical history, Math Overflow started in September 2009, so this was a fairly early question on that platform. And the question was categories first or categories last in basic algebra. I mean, that was the title of the question. There's a bit more to it. It was basically someone saying, you know, when doing this algebra course, there's category theory in it. When should I teach it? And even back then, this kind of question was felt, it's not quite what we want Math Overflow to be about. We called them soft questions in those days and tried to limit how many we had. So I kind of stepped back. I tried not to get involved with it. But the more I read the answers, the more I felt they're all quite one-sided. They were all felt like they were saying you should only study category theory if you're over 80 and preferably dead. And I didn't like that. So eventually I wrote an answer, and this question is still there. You can read the whole lot if you have an afternoon to spare. But there's one paragraph that I want to highlight for you, and I'll show you that. I'll read it out as well. I said, I believe category theory is an excellent way to understand and express mathematical concepts. I find in my own work that time and time again, when I express my ideas using categorical language, then it makes them clearer both to me and to others. Believing this, as I do, why on earth would I want to deprive my students of the same benefits? Okay, and that last sentence, there's this thing that when the question is asked, it sort of forces you to think a little bit. Any question, it forces you to think. And this question really sort of woke me up to, I use category theory in my teaching in day to day. And at that point, I was teaching linear algebra. And if you look at the rest of the answer of that, it explains sort of how that plays out in that particular linear algebra course. But it's this key thing that maths is not just this body of knowledge, but it's also my relationship to it. And I think about it in categorical terms. I think that makes it easier for me to understand. And surely if I think that, why would I want to deprive my students of that? But I came to this gradually. When I was an undergraduate, I didn't know anything about category theory. I would have been right at the bottom of almost the never heard of it. In fact, I think I probably hadn't heard of it in my undergraduate, gradually learned about it in my PhD and then postdocs, until sort of at the end of my postdoc season, I was starting to write papers in category theory. And then during my lectureship, I started working on the NLab, if you've heard of that, and was one of the main people sort of behind the scenes on it. So I sort of gradually went from the never heard of it all the way through. I've never quite described myself as a category theorist. I'm a differential topologist, but it certainly sort of almost took over my life for a little bit. But then 6 years ago, in 2014, I quit academia. I became a teacher, and I thought, well, okay, I'm going to go and teach, but higher maths, category theory, that's probably bye-bye, not going to see that. Also, I thought, until one day I was describing how to understand the formula for conditional probability, and I drew this on the board. So you've got sort of Venn diagram here with two sets A and B, and over here, you're thinking of these as the actual sets with numbers of objects in them, and then you divide by the total number of objects in your universal set to get the probabilities. Then down here, we're restricting to the universe in which B has happened, event B has happened, and then over here we want essentially the conditional probability. What's the probability that A happens given that B has happened? And I was trying to use this diagram to sort of explain that up here is sort of probability where everything's possible, and then down here is we know that B has happened and how the probabilities relate. Anyway, but as a category theorist, or not quite category theorist, looking at that, I just sat down and I thought, there's a commutative diagram. I've just drawn one of the most fundamental things in category theory on the board for my students to look at. Now, they don't know this, and believe me, I'm not going to tell them, but maybe there is something here. Maybe actually category theory is lurking inside school mathematics, and I just wasn't looking in the right place, or wasn't looking in the right way. And so I sort of started looking a little bit, and not very surprisingly, found more than I was expecting. Right, so what I'm going to do is sort of show you examples like this. But first, I know there were some people that have never heard of category theory, and I've probably gone on long enough now without explaining what it is. So I'm going to give a sort of quick overview of what category theory is and how to think of it. If it's any sort of reassurance to you, I did a practice run with this with a non-mathematician, and they claimed they got the idea, but they might have just been being nice to me. So hopefully we'll see. So a few years ago, there was a word that sort of came out in the sort of global consciousness a bit from a sort of African philosophical or cultural point of view called Ubuntu, which nowadays we tend to just associate with Linux maybe, but for a while it was sort of the word of the day. And I like to think of category theory as Ubuntu mathematics. If you look at the Wikipedia page for the Ubuntu philosophy, there's one description which is, I am what I am because of who we all are. Namely, I don't exist by myself, but who I am depends on who I'm with and who I'm relating to. So it's emphasizing community. And in category theory, we think that a thing is not what it is because of what it contains or does. So it's not the elements or the operations that determine what it is, but it's relationships to other things. So you've got to think of things not just individually, but how they all relate together. So that's category theory. At least that's category theory sort of as a philosophy, but it's also very specific then working out of that philosophy in mathematical ideas. And it's not just a sort of philosophy or way of thinking about mathematics. Well, that's very easy to find in school, in any mathematics, but it's the actual working out of that and the ideas that I'm going to show you. So here's my sort of contents for today. We're going to see an example of objects and arrows. That's a sort of basic category. I'm going to use the word arrows because I feel like throwing the word morphism, if you've never come across that, that's even more words you haven't met. So I'm going to talk about arrows. So these are the things and their relationships between them. We're then going to go to functors and natural transformations. Now, I know if you haven't met category theory, you're going, what the what? And so for that, then think about, I'm going to explain what those are in terms of school mathematics. Covariance and contravariance, and then finally adjoint functors. So again, if you haven't met these words before, don't worry. Think of this as being a sort of way of thinking about them. If you have met these words before, then this is then seeing where they come from in school mathematics. Okay, so if we're ready, we're going to start with objects and arrows, and we're ready for the second poll. Let me get that up. You can all be thinking what the answer is. The question is going to be, what is 1 + 1? So you can all be thinking what answer you're going to give, but I'm doing multiple choice. I'm a teacher. I don't allow free-form answers because you never know what you're going to get.
I'm always so bummed I can't vote in these.
You can tell us what you would vote for.
I'd probably vote for 2.
You're going for 2? Okay.
I was maybe going to vote for 2.
Okay. Well, if someone's undecided and wasn't sure, then they can cast Kate's vote for 2. That was Kate, wasn't it? I'm sorry, I don't have everyone's thing on the screen.
It was Kate, you're right.
It was Kate, great. Okay, so I'm going to share those. And yep, most people agree with Kate going for 2. A couple of people 0. Oh, one person went for 3. Oh, fantastic. I'll tell you why. I think that's fantastic in a minute. So 4 possible answers. So I figured if sort of trying to guess what you were thinking when you were voting, if you went for 0, then you probably looked at the title of the talk and went clocks. Probably clock arithmetic, modular arithmetic is going to tell us 1 + 1 mod 2 is 0. That's if that was you. Going for 2, probably thought, well, it's almost certainly a trick question, but it's too late in the afternoon to figure out what the trick is. So I'm just going to go for the obvious one. 3, I really like because when I got married, then we invited my undergraduate tutor to the wedding, and he wrote in the guest book to remember that in some axiomatic systems, 1 + 1 = 3 or more. So that's always stuck with me. So I love that one. So for me, 1 + 1, currently 5, and hopefully stopping there. And for other, you probably thought it's a trick question, but again, it's too late, and I can't even be. I know it's not going to be 2, and I can't be bothered to think of what else it is. But actually, not a trick question, or at least the trick isn't what is it, because if you ask any primary school child what's 1 + 1, they'll go, of course, it's 2, and we learn that from counting. Yeah, here's the emoji, right, for you all. 1 dinosaur + 1 dinosaur is 2 dinosaurs. 1 penguin + 1 penguin is 2 penguins. Yeah, we all know this and could recite it back in primary school. 1 o'clock + 1 o'clock is, well, what is 1 o'clock + 1 o'clock? I mean, I could put 2 clocks there, but that's not really the same as 2 o'clock. So that one's a little bit of a puzzler. What should the answer to 1 o'clock + 1 o'clock be? It's a rhetorical
This one always bothered me, that like when we add times, we suddenly start thinking one of them as an elapsed time and the other one is a fixed moment. Yeah.
Exactly. So one of the things I love about teaching in school over teaching in university is that we teach much smaller chunks. We teach a little bit of something, and then we move to something else, and then something else, and then come back round later on and kind of revisit the old things. And I like that sort of way of just continually just going a little bit further, getting a little bit further down the line. But also because in a school you teach several different year groups in one go, sometimes it can mean you're teaching the same subject to several different year groups at the same time. And just before Easter, I was teaching vectors to an age 15, 16 class and an age 17, 18 class. And that made me think not just about, one of them was an introductory course and one of them was a slightly more advanced, and made me think a little bit more about when they get into the more advanced one, how do I want them to think about vectors, and can I set it up correctly when I'm introducing it? And I was trying to emphasize the fact that coordinates tell us where we are and vectors tell us how we got there, and make that distinction. I thought that was quite an important thing. Well, it so happened that at the same time, I was doing a sort of review bit of kind of gentle maths with some age 11s, and we were just taking another look at time calculations. And it struck me that I was actually teaching the same thing to the younger ones in time calculations as I was teaching to the older ones with vectors, and that time is like coordinates, and not like a vector. And the correct thing with the correct sort of analogy of the vector was actually a duration. So we have two different notions when we talk about times. We have the time itself, which is a thing, and a duration, which is a relationship between things. And actually keeping those two apart in your mind is quite useful. It's not like a semantic thing here. It's actually separate ideas of what's going on. Where are you? What time is it? How did you get there? How long have you been sitting waiting in the queue for the supermarket? And that, in essence, is what a category tries to be, or is. It's the things, the times, and the relationships, the durations. So here's our sort of little table that on a clock we have times and durations, and in the category we have objects and arrows. And in the terms of the clock, then actually all the structure, all the interest, all the arithmetic goes on the durations. And in category theory, we tend to spend a lot more time looking at arrows, at relationships between things, than we do at the things themselves. So there's your first, so what is a category? How can I see it in school mathematics? Right back there in sort of early arithmetic, early ideas of time, but hopefully also just get a sense maybe that I'm not forcing the concepts in here. It's actually useful to think of time and duration as two separate things, and think that when I'm doing the arithmetic, I'm actually doing it on durations. And so a negative duration, for example, makes perfect sense. A negative time, no, maybe not so much. So that distinction is useful both for the students learning it as well as for me teaching it. Okay, so that was the first one. We're going to go through them fairly quickly because this, I'm not going to be able to teach the intricacies of everything in teach. I'm not teaching, explain, that's it. I've been in school too long. Right, so functors and natural transformations. Right, so if a category encodes the idea of things and relationships, so, well, if a category is a thing, there should be a way of talking about relationships between categories. So functor is just a fancy way of saying relationship between categories. And then if functors are things, there should be a way of talking about relationships between them. And that's natural transformations. So you have the category, and then between categories, you have the functor. And then between all of that, you have the natural transformations. So they just encode different levels of relationship. But in order to talk about functors, I'm going to need some categories in play to use as a sort of the example. So the two that I'm going to use in this one are sequences and real numbers. And for sequences, I'm going to use sort of affine transformations as the morphes, as the arrows. So I can relate one sequence to another sequence if I can get from the first one to the second one by scaling and shifting by a uniform amount term by term. Okay, so the A and the B don't change with the N, they're just fixed. Okay, now I don't want to go into great sort of detail about this, but these aren't unnatural in context, because effectively when we talk about an nth term formula for a sequence, we are trying to find a relationship between the sort of standard 1, 2, 3, 4, 5 sequence and our sort of general sequence that we're trying to find an nth term for. So this is not an unnatural thing. On the real numbers, I'm less bothered about morphisms, but I need arrows. Sorry, I said I wasn't going to use that word, but I need at least these ones to make it all work. Okay, right. So I need some functors. So those are going to take a sequence and give me a number. So there's very natural ones around, namely taking a sequence and giving you a particular term. Now, I've chosen the 4th term and the 5th term. And again, the point of this is not that it's there, but actually that it's usefully there, that by setting it up in this way, I'm reminding myself that the sequence is a thing and the term is a separate thing. And it's when I go from a sequence to a particular term in that sequence, I'm really changing where I am. I'm going from thinking of this as a single sequence that may have a lot of information, but as a single object, and peeling back and picking out one particular number, one particular term. So again, it's there, we talk about it, we work with it in school. I'm not imposing this language, this structure in a place where it isn't already. Okay, so those are my functors. They just take sequence, spit out a number. Natural transformation between them is the term-to-term rule. Okay, so this line here, that's corresponds to the fourth term. So this is the fourth term in my sort of base sequence 1, 2, 3, 4, 5. That's the fourth term in that one. This is the fourth term in the sequence 3n plus 7. And here's the fifth term. And as we go from this top line to this bottom line, that's the natural transformation. And when we do it on a specific sequence, all we're doing is talking about the term-to-term rule. So the natural transformation, the relationship between these two things is the term-to-term rule. And again, it's just separating out the steps of what was there already and putting them in their right sort of context and how we think about them. The term-to-term rule, it belongs to the sequence, but what it tells us is how to get from a specific term to another term. So it belongs to the sequence, but it's related to what that sequence looks like when we fixate on specific terms. So there you go. Functors, natural transformations, sequences.
So we have a sort of a big question here.
Yeah.
So should we think of this like speed, acceleration, maybe jerk, if you've heard of that one, where like we're going sort of upwards in that direction and it's less useful to talk about them? Or should we think of this more like turtles all the way down, sort of where it's the other direction? And related to that, is this where infinity categories come from?
I am not going to infinity categories. I can say that right now. If you wanted infinity categories, there was other people we should have got to talk. So I presume you mean in terms of sort of the functors of the natural transformations.
Yes.
Category theory was invented. The people that started the whole thing say they invented it to talk about natural transformations. So it came out of algebraic topology, and they wanted to talk about how to go from one homology theory to another homology theory, and in a way that sort of encoded all the structure that's in there. So natural transformations are the things that the first people that thought about this wanted to talk about. So in a way, you can think of that as kind of the fulcrum. We build up to natural transformations, and quite a lot of people sort of stop there. And then you get the people who kind of go, well, actually, we can go further up and we can start talking about relationships between natural transformations and between the things that are between natural transformations. And then you get into infinity categories. I was systems administrator for the NLab for 5 years, I think, something like that, 5 or 6 years. I never got particularly happy with infinity categories. So, they let me play in the sandpit, but what they used to talk about was sort of way above me. So in a way, you pick the level you're happy with. It goes on, turtles all the way down, but you don't have to be aware of them if you don't want to be. And certainly in this context, well, I'd love to know if there was an infinity category sitting around here, but I don't know that.
Thanks.
Does that help? Okay.
There are also now omega ordinal categories going on in the chat, so continue.
If you want to play infinite chess with categories, go for it. All right, so the next one was variance. Okay, so variance is about direction. I've talked a lot about arrows, and the arrows being the relationships. And relationships are, up to now, you could have got the idea that relationships are sort of, what's the word? They go in both directions. Mutual, yeah. If there's a relationship from one thing to another, then there's a relationship back the other way. That doesn't have to be. Relationships are directional, and sometimes when you apply a functor, the directions get swapped. So in this, I'm going to show you sort of direction swapping, and for that I need actually 3 categories. So these two are my sort of source categories, and they're both functions. Now, of course, in school, most of our functions, well, basically pretty much are x squared. We sometimes mention x cubed if we're feeling a bit adventurous, but pretty much quadratics. But in context, this would work with any function. And in the first one, I'm going to allow post-composition by a linear factor. And in the second one, pre-composition by a linear factor. So two functions, there's a relationship from one to another. If I can get from one to the other by post-composing with something of this form, and in the second one, if it's pre-composing. Okay, so those are my two source categories. My target category is shapes in the plane. Okay, and again, so long as I've got enough sort of affine transformations, so translation, scaling, I don't even need rotation, to be perfectly honest. But I can always have more if I want in the target. It doesn't matter, but I just need enough. My functor in both cases for both source categories is going to be sending a function to its graph. Okay, so if your function happened to be x squared, then I'm sending it to the traditional parabola. Okay, so function over here, graph over there. But now we have to look at what happens when I apply these transformations, these arrows. And that's where things get a little bit weird. At least I've never kind of really come up with a great explanation for why the weirdness happens, but I'm sort of hoping that having sort of thought about this in this context, I'm going to come up with one. Because when you do your function and then add 2, then that shifts everything up by 2. So the add 2 there corresponds to the translation by 2 there. But if I do it beforehand, if I did it add 2 and then apply my function, so I'm in this context, then everything's backwards. It's -2, it's going the wrong way. And the same thing with scaling, that if I multiply after doing my function, so if I multiply by 5 after doing my function, everything gets bigger. But if I do it before, everything gets smaller. So there's this shift in direction between doing things after and doing things before. And if we try and do two things at once, so we multiply by 3 and then add 2, and of course we all know, well, actually in the UK, I should have put this on the slide. Bidmass over here is, I think, PEDMAS.
MDAS?
MDAS, whatever, I don't know, something over there, but we all know we do multiplication and then addition. So this says do the scaling and then do the translation, scale then translate. But if we do it beforehand, we translate and then scale. It's the wrong way around. It's happening backwards. And that's variance. Now we have fancy words. The right way around is called covariance. That's going to go off the page. And the wrong way around is called contravariance. So we have fancy words for it, but it's basically just saying sometimes things end up going the wrong way. Wrong way down the one-way street, which can happen sometimes if you grew up driving in the UK and suddenly go to the States. As this is being recorded, I will say no more about that. But there again, okay, a categorical concept of variance is there in school mathematics. Okay, one more, last one, adjoint functors. So this, I said at the beginning, this is a series finale, or season finale. So we need the big bad. I think adjoint functors can play that role. They strike fear into the heart of any beginning category theorist. But actually, they're another one of these things that once you start working with them, then you learn to love them because they are fantastic and you get a lot of structure. A lot of things happen when you've got adjoint functors. So functors, we've already sort of talked about their relationships between categories. So adjoint functors, some special kind of relationship between categories. So I need some categories in play. Now, so far we've had clocks, sequences, and graphs. And I don't know about the US, but in the UK, this would be sort of primary school. In my school, we teach this in year 7, and this maybe in year 10. So we're sort of getting older as we go through the concepts here. Year 10 is the one before they sit that sort of compulsory exam. So looking at the sequence here, you'd be sort of forgiven for thinking that, okay, this is probably the A-level, the optional stuff that only the ones that actually want to study mathematics further can do. As a friend of mine used to say, it's amazing how wrong you can be, because we're going right back to numbers and divisibility. So my categories in play here, I've got natural numbers. Now, for me, 0 is a natural number, but it doesn't really matter in this case. And the relationship there's an arrow from A to B if A divides B. So that symbol there means divides. So if A is a factor of B or B is a multiple of A, then I put an arrow, a relationship from A to B. Now notice here, there's not going to be a relationship the other way, because if A divides B, it's highly unlikely that B also divides A unless they happen to be the same thing. So this is an example where our arrows are very definitely going one way. So that's one of my categories. The other one is multiples of 12. I picked 12 at random because it's 12. Because I thought that 17 probably wouldn't work. It wouldn't be a great one in this case. So multiples of 12. So we write it 12n as sort of every natural number multiplied by 12, but the same arrows that regardless of whether it's a multiple of 12, I can always ask, does A divide B? And if so, there's a relationship from A to B. Okay, so those are my categories. So then I need some functors. I'm going to do 4 of them because as I was sort of thinking through this example, then I came up with more than one example, and I'd like to show all of them. So I'm going to get 4 different functors, and they're sort of between a sort of scattering of these different categories. So one of them, the first one, we call it the inclusion functor. It just says, take any multiple of 12 and just think of it a number. So just forget you knew it was a multiple of 12 and just think of it as a number. Okay? That's a well-behaved functor, takes any number to itself, but instead of thinking of it as a multiple of 12, just as itself. Going back again, take any number and take its lowest common multiple with 12. Okay, it's important here that 12 is fixed. So normally we think of lowest common multiple as sort of being of a pair of numbers, but in this case, I'm fixing one of those numbers to be 12. So it's take any number and take its lowest common multiple with 12. So say if you had 8, you would end up at 24. If you had 7, oh good grief, why did I choose 7? 84? Yeah, okay, if you have 7, you'd end up with 84. Okay, so this just shifts us to the lowest common multiple. Okay, so these 2 are going to end up paired. The second 2, just multiply. Now notice these just are from numbers to numbers. I'm not particularly thinking that they're multiples of 12 here, but I just take a number, multiply it by 12, whatever it is. So even if it's already a multiple of 12, I'm still going to multiply it by 12. And then the other one, I want a division. That's multiplication. I want a division, but I can't just arbitrarily divide because I want to do it to all numbers. So instead of arbitrarily dividing, I'm dividing by the highest common factor of that number with 12. Okay, so that's always going to work because the highest common factor of 12 and A is definitely a factor of A, and so that division works. Okay, and it turns out that these 2 are adjoint functors and these 2 are adjoint functors. So what on earth does that mean? Well, we write it in this funny way. What that means is they've got a very special relationship with each other, that they are sort of inverse, but inverses don't necessarily exist, so they're the closest thing you can get. So this first one, this first adjunction, the way I like to think of it is that the nearest multiple of 12 to A is 12A. So it's almost like you put all the multiples of 12 in N, and then you ask each number, whether it's a multiple of 12 or not, to move to the nearest multiple of 12. And so you kind of think you've got 8 there, and you're going, right, move to the nearest multiple of 12. Well, 8 can only move along arrows. So 8 can move to 16, or it can move to 24, or to other multiples of 8. This is really too late to be doing mental arithmetic. And we say move to the nearest one that's a multiple of 12. Well, it's going to move to 24. And that's what the lowest common multiple is doing. And that's really what this adjunction is just saying. It's just saying that there's this relationship between multiples of 12 and the lowest common multiple. The second one is maybe, it's a little bit sort of weirder in terms of what it is, but actually the relationship is possibly easier to understand, that it's saying that division by the highest common factor is the closest thing to an inverse that you're going to get for multiplying by 12. Okay? There is no inverse to this because there are numbers that don't divide by 12, but there's a sort of next best thing, and that's dividing by the highest common factor. So it sort of tells you this sort of adjunct, fact that these are adjoint functors tells you about the relationships between these things, and therefore about how to understand them and how the structure works and what structure they have, what structure they preserve, and just a little bit more tools for working with them. Right, there we had 4 category concepts in high school maths. Actually, that doesn't work. High school math or secondary school maths. We'll do one or the other. So this is the end of the sort of mathematical part. There's a little bit more to come, but we're done with the sort of maths on this. So I just, before sort of doing the kind of conclusion-y bit, I just want to go back to the kind of where we came in, call it the aims and objectives if I was being sort of a proper teacher. And so I hope that wherever you were on this sort of poll that I put up originally, that, well, kind of, I hope that you kind of got that red line that you can say, okay, I've never heard of it before, but I saw maybe a few bits about what it's about, maybe not all of it, but some of it. So if I've managed to tick some of those off for you, especially this last one, then I've kind of met some of my aims and objectives. But like I say, there's a few, I've got a sort of few concluding remarks. But maybe if there's any burning questions that would be at this point before I kind of go to concluding remarks.
We spent a while trying to figure out the fractor letters, and I think we've successfully managed that finally.
Oh, sorry.
It's okay.
They're
very reasonable. It just took us a while.
I mean, I possibly should have thought about that better. I mean, my favorite thing that I ever wrote was this thing on mathematical calligraphy, which you can find on my webpage. And in there, then I do kind of say, basically, don't use obscure letters in your fonts. And yeah, I've just done it. Sorry.
Okay.
Next time, just use emoji figures. We just like, instead of a fractor L, like just put a penguin there and we'll be like, oh yeah, it's a penguin functor. It's fine.
That is a fantastic idea. Right.
You're welcome.
Okay. Can someone please invent time travel so I can go back an hour and just change my slides?
No, like 4 slides ago, you said you couldn't go back, like a negative time didn't make sense.
No. A negative duration makes sense. A negative time doesn't make sense. Anyway, right. So okay,
we have a couple of thoughts, okay. but they seem like after your conclusion.
Okay, let me do the conclusion, and then we can hopefully have a bit of time for questions. And maybe just we'll answer 1 or 2 of them. So I think there's a sort of so what kind of coming out of this. And I thought a lot of different ways of sort of summing up and concluding what I want to say here. I think, first of all, I want to make sure it's clear what I'm not saying. I am not saying that we should teach category theory at school. Okay? I am not saying that. I'm not saying that, but I am definitely not saying that. And if you want to propose category theory in the curriculum, please make sure you explain what you're going to take out, because frankly, there's far too much in the UK curriculum as it is, and I'm pretty sure the same would be true for the US. So I'm not saying that. I saw this picture on Twitter earlier this week, and I was absolutely determined to get it into this talk because I think it's fantastic. And so this is slightly sort of shoehorning it in here, but it was this. We have this sort of picture of sort of school maths, this completing the square in school maths as rewriting a quadratic, grad school math, completing the square, doing commutative diagrams. And I thought this was sort of brilliant, particularly given this talk of trying to bring these two together in some way. But my answer to this is not to sort of take this, which is a beautiful bit of category theory, and try and put it into there. Okay, so I'm not saying that. The other thing I'm not saying is that maths teachers should know category theory. Okay, I do, and I find it useful, but I don't think that forcing any particular area of mathematics onto teachers is actually a good thing. It works for me because it's how I think about mathematics, but that's not going to be true for everyone else. And if you sort of make it a condition of being a teacher, they've got to learn category theory, my word, that's not going to do great things for our profession. So, I mean, if you want to take something out as sort of what maths teachers should have, it's maths teachers should have more time so that they can explore the areas of maths that they like and do more of Katrina's puzzles. But, you know, while I'm wishing for a unicorn, then I'd quite like, 3 of them. So, you know, we're never going to get more time for maths for teaching. So that's pie in the sky. Okay, so what am I saying? Well, the street I grew up in has its own Wikipedia page. There's a little fact for you. It has nothing to do with the fact that I grew up there, but that it was the last place of residence of one of Oxford's more famous professors, actually, residents. And whether you like hobbits and elves and dwarves or not, or you just can't stand them, and when your partner says they want to do a Lord of the Rings marathon and watch all the films, you go out for the week, doesn't matter. One thing that it's very hard to deny is that he knew how to tell a story and he knew how to craft a world. I'm talking about Tolkien, for anyone who hasn't quite clicked. And one of the things is you can read The Hobbit and know you've read a story and not feel like you've missed anything out. But you also get a sense of there being this world behind it. And then maybe you go on and read The Lord of the Rings and you get more of a sense of that world behind it. But it's consistent with what you already knew from The Hobbit. And then possibly if you're a masochist, you read The Silmarillion and you discover that actually this world behind was immense. And so kind of that's the picture I want to give you. I want to tell a consistent story. When I'm teaching, when I'm trying to explain mathematical concepts to my students, yep, I'm telling them The Hobbit. I'm telling them a story that's at their level. But I want it to be consistent with what they will then go on to see if they go on to study maths at a higher level. If one of my students goes on to do a degree and hopefully more, then what I want is for them to come back to one day and go, I see how what you said connects with what I now learned. Okay? So it's not that I'm teaching them higher, more advanced concepts, but what I teach them is consistent with those things. That's maybe for the sort of ones that maybe I'm thinking might go on, but also it helps with the students who, here's one of the sort of themes. There was this phrase came up a couple of weeks ago. I can't remember off the top of my head who said it, but multiplying by -1 shouldn't be scary. And my immediate reaction to that was, have you met my students? I mean, if any of them are watching, I'm joking. But actually some people don't like multiplying by -1. And for them, the structure is hard to get. And for those students, I find that the way that I look at maths is to reduce it down to the what's really going on in any particular concept. And category theory, I find, helps me do that. I have a phrase that sort of sits at the back of my head. Sometimes with these phrases, it's kind of better if they're in a foreign language, and Norwegian is my sort of second language. So my phrase is, hva er det egentlig? Which means, what is it? Really, really, really deep down, what is it? And so when I'm trying to think, how am I going to explain this concept to my students who perhaps, maths isn't their favorite subject, then sometimes I'm trying to think what's really going on with it is what I'm trying to, is where I try to go with that. And lastly, what I really hope is that I've shown you that you can find your maths in school maths. I'm sure a lot of people, as I was talking through examples, were going, hey, but that's not category theory, that's linear algebra, that's geometry, that's probably not algebraic geometry, but possibly somewhere. Of course it is. It's not one thing, but you can find it there. And when you talk to students, it's what I think is it's best to find your maths in theirs, connect where they are, show them how what you do relates to what they are doing at that moment. And that's what I had to say today. So thank you very much, everyone, for listening.
Shall we unmute and thank Andrew?
Great job.
So one of the questions that was partially answered in the chat was if somebody wanted to go from never heard of it to now they're aware that it's here, do you have any suggestions for places to start reading or looking?
That is a question I really should have anticipated, isn't it? Actually, I did see someone mention on Twitter, I think it was actually Katrina, the books by Eugenia Chang. She tries to put category theory sort of out in the world and show the ideas. I think it's still, I haven't read all of them, but I think it's still, that's you're not going to get into the sort of nuts and bolts of it from reading her stuff, but it will certainly be a good introduction. I think it is one of those things where you need to find examples that you already know. And so therefore saying, look at this book, if it's not kind of in your rough area already, then it probably won't be a very good book to look at. So I kind of don't have a good answer for that. I learned it because I needed to understand the stuff that I was working on at the time, which was loads of stuff in algebraic topology. And the more I learned, the more I found that it just fit my way of thinking. Mm-hmm. I think, so I'm afraid I don't really have a good answer to that one.
Well, there were a couple of resources in the chat,
great.
so that's partially answered.
Okay.
And I went to a great talk by Emily Reel, I think, about associativity. At I forget, time doesn't mean anything anymore. Maybe last year at Math Fest.
Yeah, so I think it was a couple years ago. Well, I don't know. I saw her speak a couple years ago, 2018 in Denver, about the distributive property.
Emily is here, I think. So if she'd like to say something.
She dropped in.
Oh, it was fantastic.
Right. Well, in that case, I'm stopping talking, and she can take over.
Sorry, I'm a little embarrassed by that. Actually, I'm late because I just gave a version of that talk to some REU students. But the slides are available, and I'll remind myself where they are, and I'll drop the link in.
That would be great.
That would be brilliant.
Other questions? Oh, the other one from the chat was, I know you love to talk about how to make the tech work in the chat during these talks. So do you have any, so if we can talk about category theory first, but people would be interested in hearing about it. Emoji, apparently.
Emojis?
Yeah.
So I guess the main thing is I use Lua LaTeX so that I can get good font support, and I'm on the most up to date. And then actually I just cut and paste. So you have to load a suitable emoji font, which on my Linux machine was something like Noto or Noro. Something there's a standard. So you will have an emoji font, and if you use Lua LaTeX, it's really easy to load any old font, and then you can actually just almost cut and paste the emojis into your document. It looks really weird in Emacs, but it comes out quite nicely. I think that's one I'll post the source, not the source code for this, but for an emoji, I did a sort of sample thing for a guy in Sheffield earlier this week, and I can just post that on Twitter.
Great. Hannah, I see you're unmuted. Did you have a question?
Oh no, I think I was just still unmuted from.
Okay, great. So does anybody else have a question? If not, I have one, but I can talk to Andrew anytime.
Well, so can anyone. I mean, yeah.
BK, what is your question? I would love to hear your question, BK.
Okay. Well, so I taught high school 2 years ago full time, and my proudest day, I was working with juniors, and they'd done this activity where they approximated the surface area of a sphere by taking the difference of two volumes of concentric spheres and then dividing by the sort of thickness of that shell to get an approximation for the surface area. And then on an assessment, my co-teacher and I wrote a thing where we asked them to apply the same strategy to compute the surface area of a cylinder. It's much harder, which I didn't really realize until in the thick of it, because there's two variables and changing. And if you only do the radius changing, you get the outside. If you do them changing at the same rate, you get the top and the outside. And then if you think carefully about how this one changes once and this one changes twice, you can make it work out. So we spent an extra day where the goal was to have them present all four of those arguments together. So they presented all four of those at the same time, sort of one level abstracted up. And then they like way exceeded expectations, where they brought in things like, oh yeah, this is like where we have a name for the play on the basketball team, but the details are a little different in each kind. Or somebody brought in an example from Con Law that they had started a little Con Law publication, and I was just so impressed with them. So I guess the question is that the sort of thing you're thinking about leveraging this sort of categorical kind of perspectives in secondary context? Was that just a fun example?
I think that's a great example of the sort of broader idea that I try and do that I'm trying to talk about, that is, so I mean, I guess the thing with the surface area of the sphere is sort of, you know, that is how it works when you start talking about calculus, and so there's a sort of foreshadowing there. I mean, it sounds like it then went on brilliantly, and I wish my lessons were like that. But
we're a really awesome
there is
group.
And there are sort of aspects of this sort of structural way that actually do sort of feed into education theory. But it's an area that is on my list of things to do and read is ridiculously long. I think we need the infinite chess back to measure how big that to-do list is getting. But the way of structuring ideas and a hierarchy, I think, yeah, there is a sort of categorical aspect that can be used there. What that is, I don't know. I mean, so a lot of these things, a lot of what I'm sort of talking about today is just kind of ideas I've had that, by giving this talk, it's sort of forced me to polarize them a little bit, and to, well, not polarize, crystallize them a little bit, and to give them a bit more shape. But they're still, for me, very experimental and experiential, and I would love to kind of find people who would love to talk further about some of these ideas, not necessarily category theory, but about reconnecting the different levels of mathematics and thinking what's appropriate at the different levels, that when we lie to our students, we're not really lying, we're just telling them stories that they will then learn the kind of background from later on. So I would love to have those conversations with people in the future. Absolutely.
Great. We have time for one more question before we have to stop the recording. Anyone want to jump in? All right, well, I'll do a little wrap up, and then I want to pick Andrew's brain. So
yeah, I'm happy to stick around for a bit after the recording ends. Yeah.
I just wanted to remind everyone that we're taking a 2-week break. Talk Math with Your Friends, summer vacation. But come back on July 16th for My Favorite Theorem live, and you can always see the archive of our talks. Not all of them are recorded, but the ones that are recorded on our YouTube channel.
We do have some more. We have some more talks in the works, in the oven. They're still baking, right, for coming out after July 16th. We just haven't released our full schedule, but we definitely have talks through the end of July and into August in the works, and perhaps beyond then, as we all prepare for the start of our fall terms. We'll have to figure out what that's going to look like. But we don't have any intention to have just one more talk and then have this thing in.
Sorry. Yes. All right. Well, please join me in unmuting, and thank you, Andrew, one more time.